Hello, my name is Askeland. This is my 10th video about Riemann's hypothesis. In this video, I'm going to show polar plots of the Euler product and of Riemann's analytic continuation. Then I'm going to show how the plots are simplified with Askeland's condition. In the polar plot on the right-hand side, you can see how the red curve loops around the blue curve. The blue curve is Riemann's analytic continuation. The red curve is the Euler product. Both curves pass through zero for some values of the variable b. These are Riemann zeros, which are listed in the upper left corner. In the lower left corner you can see plots of the phase diagrams, which are only the angles of the functions. Notice that every time the polar plot has a zero, the phase diagram does a pi radian phase jump. For a real variable x, x minus 1 is a factor. This factor is 0 when x is 1. The factor is positive when x is larger than 1. The factor is negative when x is smaller than 1. When x passes through 1, the angle goes from minus 180 degrees to 0 degrees. The change of angle is 180 degrees or pi radians. A complex valued function will also have the pi radian phase shifts as the function passes 0. But the start phase can be any angle. This is Riemann's first zero at 14.13. You can see the phase shift of pi radians in the phase plot. In this plot, the phase shift goes from 300 degrees to 120 degrees. This is the formula for the Euler product, P is prime. The maximum prime is 997 for the red plot in this case. S equals 1/2 plus I times the variable b. This means that we are on Riemann's critical line. So the red polar plot is made with this Euler product. Use all primes up to 997 and calculate the product. Plot the result for b between 12 and 50. The only way this product can be 0 is as the limit where the denominator becomes infinitely large. But then we need infinitely many primes. So let's study what's happening when we increase the maximum prime by a factor of 10. Now the max prime of the Euler product is 9973. We should get approximately the same numerical zeros. We get the same zeros, but now the amplitude of the phase oscillations of the red phase plot has increased. Here you can see that the Euler phase reaches a maximum. And this is the corresponding location in the polar plot. This phase is approximately 1.7 radians. The phase of Riemann's analytic continuation is approximately 1 radian, which is the phase of the blue line in the polar plot. In this case, the phase plots have approximately the same phase, which means that the phases in the polar plot should be approximately the same. which is the case. In this slide, the Euler phase has a minimum. And has now moved over to the other side of the blue line of Riemann's analytic continuation in the polar plot. So let's look at what's happening with the phase diagram as the maximum prime is increased from approximately 10,000 to around 10 millions. Two things happen. One, the amplitude increases. Two, the oscillation frequency increases. As the maximum prime increases even more, Riemann's analytic continuation is drowned in phase waves. Wouldn't it be nice to have a mathematical tool which could find the zero crossings of the oscillation? And that tool seems to be the solution of this equation. I call this equation Askeland's condition on phase form. I have given a proof that Riemann's functional equation can be seen through the multiple solutions of this equation. Here you can see that I solve Askeland's condition for different values of the maximum prime. And I land on Riemann's analytic continuation. The phase waves are gone. But I get a more discrete plot. But as p increases, the plot becomes denser. Now Askeland's condition has been applied to the plots. The phase plots are now approximately the same. You can draw a line from 0 through both dots in the polar plot, and these dots will pass through Riemann's zeros simultaneously. I'm going to end this video with one more plot where Askeland's condition has been applied. Here I find all the zeros up to imaginary part 100. I have increased the max prime to around 100,000. For every phase shift of pi, the two dots in the polar plot go through 0. Thank you for watching.